In this video, we discuss how we can compare segments when the dependent variable is quantitative in nature, for example, expenditure on the product category. We will consider first only the case where there are two segments. If you have more than two segments, you'll need to use ANOVA, which we will discuss in a later video. There are two types of tests you need to learn about. The first is a two-sample t-test, also known as an independent samples t-test, which is used to test if two populations or groups or segments are different from each other on some variable. The question we are asking is the mean for population 1 equal to the mean for population 2? Some examples of this might be if we ask whether men and women drink different amounts of coffee or spend different amounts on athletic shoes. The second type of test involving a difference of means is a paired t-test, also known as a related samples test. This is used to test if the mean changes in a given population. The question we are asking is the mean for one set of observations the same as the mean of a second set of observations from the same source? Some examples. Does blood pressure in a group of patients change after taking medication? Here, the source of the data is a group of patients. Or we could ask, do sales in a store change after a price cut? Here, the source is a set of stores. Yet another example, does preference for a brand differ from preference for another brand in a group of consumers? Here, the source is a group of consumers. Let's look first at the two-sample t-test. The basic idea is that there are two separate samples drawn from two different populations, and we test if the means from the two populations are different. The null hypothesis is that the means of the populations are equal, that is, there is no difference in the population means. The variances of the two populations are unknown, but in order to test whether the means are different, you have to assume either that the variances of the two populations are equal or that they are unequal. This assumption is required because part of the formula for the test depends on what you assume. If you assume equal variances, you can conduct an ANOVA test instead because it gives you the same results. But if you assume unequal variances, you only have the option of doing this t-test. In practice, this often does not matter because in many cases, the conclusion is the same regardless of which assumption you make. The test statistic is a t-statistic if the sample size in either group is less than 30. If both samples are at least 30 in size, it is distributed as a z-statistic. The formulas look a bit ugly, and I'm not going to repeat them here since you can look them up, but you don't need to know them because SPSS comes to the rescue and does the test for you. Let's look at the data from the national insurance case. The question we want to answer is there a difference between less educated and more educated respondents, that is, those with education equals 1 and 2, and those with education equal to 3 and 4, in their ratings for overall quality? The H0 is that there is no difference, and the alternative is that there is a difference. We need to compare the mean rating for overall quality for the two groups, so a two-sample t-test is needed. In SPSS, click on Analyze, then Compare Means and Proportions, and then on Independent Sample t-test. Define the test variable, the metric or the quantitative variable you want to calculate the mean for, and the grouping variable. In this example, the test variable is OQ and the grouping variable is ED. Next, define the groups for ED by specifying the cut point equals 3. This will define group 1 to contain anyone who checked values 1 or 2 for ED, and group 2 will be anyone with values 3 and 4 for ED. Click Continue and OK. Now let's look at the results. The first thing to look at, as always, is the p-value for the test. Is it less than alpha? If the answer is yes, then look at the means for the two groups to see how they differ. Here are the results. The second table, titled Independent Sample t-test, shows you the results of the test. The two rows in this table show you the p-value under different assumptions about the variances. The first row shows the p-value assuming equal variances in the two groups, and the second row shows the p-value when you don't assume equal variances. Notice in this case, the p-value is less than 0.01 no matter which of the two assumptions you make. In practice, this often turns out to be the case. Since the p-value is less than our alpha, we reject the h-naught that the means are the same. Now we can look at the means shown in the first table. You can see that the mean for the group greater than or equal to 3 is 7.18, which is lower than 8.15, the mean for the less than 3 group. In other words, the first group, which has higher education, gives a lower rating on overall quality than the second group with less than a college degree. This suggests that national insurance is rated more poorly among college grads. This implies that unless they take action to improve their quality perception in this group, they may lose more of these customers. In closing, we should consider what we would do if the p-value for the test led to different conclusions for the two rows, equal variances assumed and equal variances not assumed. What if one p-value was greater than alpha and the other one was not? In this case, we would need to choose the assumption to make and then look at the p-value under that assumption. In this case, we would need to look at the third table, titled Homogeneity of Variance Test. This shows the results for a test of the hypothesis that the variances are equal in the two groups. As always, we look at the p-value, and if it is less than alpha, we reject the null hypothesis of equal variances. As you can see, the significance or p-value for the test is 0.015, which is less than our usual alpha of 0.05. So we would reject the hypothesis of equal variances. Going back to the middle table, we would look at the second row only, that is, when equal variances are not assumed. That would give us the correct p-value of 0.003, and that's the one we would use. Again, this last step is rarely needed because in most cases the two assumptions would lead to the same conclusions. But if they do not, you should look at the bottom table to figure out the correct assumption to use.